It is cat o'clock and mic stand o'clock. And we're going to do some applications of polynomials. So eventually in calculus, we can find the maxima and the minima, also known as extrema, with calculus. And it won't be too bad. It's just a little calculus. It won't be too bad. But in the meantime, we're going to use Desmos to find the maximum and the minimum. So an open top box is to be constructed by cutting out squares from each corner of a 14 centimeters by 20 centimeters sheet of plastic and folding up the sides. Let's get a picture. What the heck's going on here? We have a sheet of plastic that's 14 centimeters by 20 centimeters. We're cutting out squares from each corner. Kind of like this, cutting out those squares of each corner. And then we're folding up the sides. Oh, okay, so if you look at this inner figure, right? Once the squares are cut out, it looks like this. So we're folding up the outsides of that red part. Okay, got it. So the question is saying, okay, find the size of the squares that should be cut so we maximize the volume. This is kind of sounding like an optimization problem. Kind of sounding like chapter 3 stuff. So how do we model this? Well, whenever we have an application, a good choice of variable is just what it's asking us for. What is it asking us for? Find the size of squares. That's what our variable should be. So let's let x be the size of the square. And it's a square, so it doesn't matter whether it's the horizontal distance or the vertical distance. Squares are square. That tells us what x should be. What do we want to maximize? The volume. So we want to maximize the volume. What is the volume of a box? Well, volume is length times width times height for a box. That's too many variables. We're only graphing functions of one variable here. Well, okay, what are these things? What is the length? What is the width? What is the height of this box? If we fold this up, right? If we fold this box, this is the base of the box, right? Because we're folding up the sides. So it's going to look something like this, right? And then it's like going up. Like this. My box is on its side for some reason. Don't judge my drawing skills, please. So, yeah, right, that's maybe not helpful. Yeah, we're folding things up. So the base of the box, the length of the base of the box, is that length of that red bottom. What is the length of this red bottom? Well, it's almost 20 centimeters. But we cut out an x here, and we cut out an x here. So the length is 20, but we made it shorter. We lost an x, and then we lost another x. Right? This is our length right here. And our width is similar, right? The width used to be 14 centimeters. But again, we cut out 2 x's of it. What's the height? When we fold it up, the height of the box is going to be this guy right here. This guy right here. This guy right here. These are all the heights of the boxes. How big is that? It's x. So the length, the width, and the height are all x's. So our volume is length times width times height. Hey, that looks like a polynomial. What a coincidence. What a coincidence. Who put this problem there? It was me. I did. Or maybe it was the book. Maybe I've stolen this problem from the book. All right, we want to find the max, the biggest this can be. Later we'll use calculus, but here we're going to use Desmos. So let's look at this function. What does this function look like? 20 minus 2x 14 minus 2x times x. Well, where is this function the biggest? I've got no clue. I can't see a thing. Let's zoom out. Oh. So zooming out, really kind of hard to see. Let's keep y zoomed out, but let's change our x's. We know x can't be smaller than 0. And the biggest square that we could cut out, right, would be 7. Right? Because if the square is bigger than 7, then this side doesn't exist anymore. It has to be between those two things. And oh, look at that graph. That is looking nice. You're a nice looking graph there. There's some pickup lines along the lines of that. This is where the volume's the biggest, right? The input is x, the size of the square, and the output is v, the volume. That's going to be the biggest when our input is 2.7, when we cut a 2.7 inch square. And the biggest volume is going to be 339 centimeters cubed. All right, so size of the square, the volume is biggest. When x is about 2.7. So when we have squares, or when we cut squares of about 2.7 centimeters. That's what it asked us. It asked us to find the size of the squares that should be cut. All right. There we go. We did it. And again, we know the maximum possible volume, 339 centimeters cubed, but we weren't asked that. What are the maximum and minimum values of some function f on certain interval? Well, let's find out. Let's graph it. Negative 0.2 times x minus 2 cubed. X plus 1 squared. And x minus 4. And, oh gosh, we're going to need a... Oh, you can't see anything. Really need to fix my green screen before the next video. So let's zoom in the right way. Okay. X, we said, was between -1 and 4, I think. Yep. And y, well, we need to zoom in on y. Let's say -10 to 10. Oh, okay. So on this interval, what's the biggest we can get and what's the smallest we can get? Well, the biggest is right here. Smallest is down here. What's the question? Maximum and minimum values of the function. The biggest a function ever gets is an output of 6.951. The smallest a function ever get is a function value of -6.474. All right. Well, we could say when this happens, we could, if it specified when do these maximum values happen, then we could talk about the x. But it says, what are the max values? The max values of the function's all about outputs. There you have it. That's our answer. That's the biggest this function gets on that interval and the smallest it gets on that interval. As a side note, look at our zeros. This 0 has multiplicity 2. This 0 has multiplicity 3. This 0 has multiplicity 1. It all ties together. Next video, I'll do some homework problems and fix my green screen. Stay tuned. Bye-bye.